this course, we will take you on a virtual tour to see how electrical power is distributed throughout a building. This is defined as the electrical distribution system. These systems are uniquely comprised of a variety of electrical components to meet specific electrical demands. You will learn the function of each of these electrical components and how it relates to the total operation of an electrical distribution system.
In our example, we begin with the utility company supplying 13,800 volts from the road to a utility pole in the parking lot. At the top of this pole, you see 3 transformers. These transformers will step down the 13,800 volts to 4,160 volts. This voltage is transferred down the pole through copper wires that are encased in conduit. This conduit travels underground and enters the oil transformer on the high or primary side of its junction box. Let's look at how the oil transformer works. The junction box receives the incoming power on the high or primary side. It enters the transformer through insulated copper connectors. Notice there are 3 wires. This is our 3-phase system. There are 3 windings, one for each of the wires or phases. The wires are connected to the top of the windings. The windings in this transformer will step down the voltage to 480 volts. Notice that the incoming wires that are carrying the 4,160 volts are smaller than the wires at the bottom carrying 480 volts. This is because the amperage increases when the voltage is lowered and vice versa. Higher amperage generates more heat and requires larger wires. Wires connecting to the bottom of each winding will then return to the low or secondary side of the junction box. From here, the wires will pass through conduit and travel underground to switchgear for further distribution. The oil in an oil transformer is used for cooling. The core is filled with non-conductive oil. In most cases, mineral oil is used. Traveling through fins cools this oil, which utilizes the conduction process. Usually there are no pumps in smaller oil transformers. In addition to fins, some larger oil transformers will have exterior fans with thermostats that blow additional cool air over the fins. Oil transformers are placed on a concrete pad and almost always located outside the facility. This is in part due to a high fire risk. What is switchgear? It's the beginning of the electrical distribution system inside the facility located in an electrical room. It is made up of several sections containing switches and/or breakers. The first section receives the incoming power from the oil transformer. The wires are connected to a main breaker, or in this example, they are attached to fuses. The fuses are connected to bus bar. Bus bar is either made up of copper or aluminum. The voltage travels through the bus bar to each section of connected switchgear, energizing each section. Here in our example, we have switchgear that is rated at 2,000 amps. It consists of 5 sections connected together. As you can see, section 1 contains the incoming voltage connected to the main fuses. These main fuses protect the downstream electrical equipment within the switchgear from exceeding 2,000 amps. In the event that more than 2,000 amps are drawn, these fuses will open and disconnect voltage. Section 2 and 3 both contain a draw-out breaker. A draw-out breaker is a large disconnect switch that has a designated amp rating for a specific circuit. These breakers are large and heavy, which require them to be on casters which run on tracks. This allows easy removal for maintenance and repairs. You can see the draw-out breaker in section 2 is connected to the bus bar that is traveling up into bus duct. Section 3 of the switchgear contains the second draw-out breaker. You can see that the bus bar connecting to this breaker is not attached to anything. This is a spare breaker designed for future expansion of the facility. Section 4 contains 6 molded case circuit breakers. These breakers have a lower amp rating than draw-out breakers and are not as heavy. This allows them to be directly bolted to the bus bar. Remember, all breakers have the same function. They are to disconnect voltage when amperage exceeds its maximum rating. The 5th and final section of this switchgear is empty with a solid or blank panel cover. This could be a spare section for future expansion. A blank front does not necessarily imply that the section is a spare. It is important to ask what is the function of this section and is there something in there that needs to be tested. Our draw-out breaker in section 2 is connected to bus duct. Bus duct is a rectangular or square metal enclosure containing bus bar. Its purpose is the same as electrical wire and conduit, but is able to handle larger amp ratings. Bus duct is made up of 10-foot sections. Plugs or connectors are spaced every 2 or 3 feet for the purpose of attaching fused disconnect safety switches, which can then supply voltage to designated areas. In our example facility, you see the bus duct rising vertically to the roof. It passes through an electrical room on each floor. These rooms generally house breaker panels, 1 or more transformers, and/or disconnect switches. Power is then distributed throughout the floor. The bus duct reaches the roof to supply power to HVAC systems through a disconnect. A distribution switchboard, a distribution panel, and a branch circuit breaker panel all have the same functionality. They can contain many circuit breakers distributing voltage to all areas of the facility. What differentiates them from each other is their amperage rating. Distribution switchboard is an electrical panel with an amp rating between 1,201 and 1,999. A distribution panel has an amperage rating of 401 to 1,200. A branch circuit breaker panel has an amperage rating that is equal to or less than 400 amps. The dry transformer has the same function as an oil transformer. It steps down voltage. The difference is that the dry transformer uses air for cooling instead of oil. As the transformer heats the air inside, cool air is pulled in at the bottom. Heat rises through a natural convection process and exits from the top. Dry transformers generally are used to step down 600 volts or less. Please note that transformers can be used to step up voltage or maintain a certain voltage. In most cases, transformers are used to step down voltage. An automatic transfer switch monitors the incoming power from the utility. If there is an interruption, it will send a signal to start an emergency generator. Once the generator reaches a desired voltage level, the ATS will switch over to the emergency power. There is a slight interruption in power from the time the ATS switches over to the generator from the utility power. In facilities such as data centers and hospitals where uninterrupted power is very important, a battery bank is in place to provide power until the generator is able to supply the correct voltage. Once the power from the utility is restored, the automatic transfer switch will automatically switch back to normal power. This emergency power generally feeds specific circuits. In some cases, it may supply the entire facility, but this is not the norm. In larger facilities with higher emergency demands, you may find several generators along with several automatic transfer switches. Auxiliary power is also stored in a battery bank. A battery bank is located in a designated room with battery racks that house batteries that are connected together. They are being charged 24 hours a day. These batteries are connected together to provide a specific voltage for a certain period of time. Almost every facility, there are electric motors. Motors are used in pumps, machinery, conveyors, elevators, and the list is endless. In order to distribute power to motors, the electrical distribution system has motor control centers, or MCCs. These MCCs are made up of a series of sections. Each section contains buckets. Each bucket is assigned to a specific motor. A MCC bucket contains many things to operate the motor. There can be computer logic boards, or PLCs, transformers, contactors, and other control devices to operate the motor. For the purpose of electrical distribution, we only need to focus on a few components that relate specifically to the electrical. Each bucket has a disconnect switch and a breaker. The breaker is designed to trip if the power exceeds the recommended setting. The disconnect switch is there to manually turn off the power to the motor. There is also a combination motor starter. These consist of the same disconnect switch and breaker, but also has two other features. It has a start-stop switch to manually turn the motor on and off. It also has a hand-off auto switch. When this switch is in the auto mode, it allows another source to control the motor. A good example of this would be a sump pump. A float switch that is switched on by rising water will control the sump pump. The motor will be turned off when water levels go down and reset the float switch to the off position. When this switch is in the hand position, the motor is always on. Power distribution units, or PDUs, are found in data centers and computer rooms. Each of these units contains one or more circuit breaker panels and a transformer. They provide clean power to computer servers. A disconnect switch is nothing more than a switch designed for specific voltages and amperages. There are many different types and sizes. Some disconnects have fuses in them. The electrical distribution system will have a unique layout for each individual facility. You will not always find every type of electrical component that we reviewed or the same configurations in every electrical distribution system that you examine as well. The key to identifying each layout is to begin at the incoming power source and identify each component and location as it distributes electrical power through the facility.